Hi, everyone. Welcome to the first talk of the semester. We're starting things off right with Sunita Chepuri from Minnesota, who'll be talking about Kazhdan-Lusztig Immanents for K-positive matrices.
Yeah, thanks to the organizers for inviting me. I'm actually kind of at Michigan now and also kind of at ISERM. I just graduated, so now I'm a postdoc at Michigan, but also this semester a postdoc at ISERM. It's confusing. I have many affiliations. Um, this work is joint work with Melissa Sherman Bennett, who is a graduate student at Berkeley. And I just want to say that you should feel free to at any time interrupt me if you have questions. I have the thing minimized, so I can't see if you like raise your hand or anything. So just jump in if you have questions.
I can
Okay.
also read the chat if anyone doesn't want to verbalize a question or can't. So if you ask in chat, I'll just ask for you.
Okay, great. Okay, so here's an outline of what we're going to do. So we're first going to start off with an overview of total positivity. And then we'll be talking about what are these immanent things that I have in my title here. And so those are sort of like the background sections. And then we'll be getting into what was the main question we were looking at and what are our results. Okay, so we're starting with an overview of total positivity. So in general, if we have a matrix, we can choose some, can you see my mouse if I'm moving it? I'm going to hope yes, because no one said no.
Yes.
Okay. So we're going to take some subset I of the rows and J, a subset of the columns, and we'll say M sub I with the J on top, is the submatrix where we take all of the rows indexed by I and all the columns indexed by J. And if I and J are the same size, then we can take the determinant of such a submatrix, and that is called a minor of M. And a matrix is totally positive if all of these minors are strictly positive. So here's an example. Hopefully I computed all these determinants correctly. But we can see just right away that all of our size 1 minors, so that's where like I and J were both size 1, those are just the entries of the matrix, and those are certainly all positive. And I computed all the 2 by 2 minors. There are a bunch of them. And also there's only one size 3 minor, the whole determinant, and that's 8. So we can see all of these things are positive. So M is totally positive, unless I made an error, which is certainly possible. Okay, so why would we care about these sorts of objects? So in general, in this talk, we are going to be talking about totally positive matrices where our inequalities have to be strict. Just for this one history slide, I am going to bring in the totally non-negative matrices, which is when we don't require that strict positivity, just non-negativity. So the first time that these totally non-negative matrices showed up is in work of Schoenberg. He was looking for matrices that have something called variation diminishing property, which essentially means if you have a vector, when you multiply that vector by a matrix, the number of sign changes in the vector doesn't increase. And so these totally non-negative matrices came up in this case. And at around the same time, the totally positive matrices came up in a completely unrelated context. Gontmacher and Krein were looking for matrices that have nice eigenvalue properties. So totally positive matrices have the nice property of, if you have an n by n totally positive matrix, a real totally positive matrix, it has n distinct real eigenvalues. So these two things came out at around the same time and kind of kicked off this field of total positivity, which people say sometimes to refer to both total positivity and total non-negativity. And totally positive and totally non-negative matrices have since then been found to have sort of all sorts of uses in a wide variety of areas of math and physics. But I'm a combinatorialist, so you might be asking, well, none of these things sound like combinatorics. Why would a combinatorialist care about this? And one of the main reasons that total positivity ended up as a topic in combinatorics is because they had this combinatorial relation to networks. I cited Lindstrom here. Some people might prefer Gessel-Viennot, but generally the idea is if you have some directed network with non-negative weights, you can sort of turn that into a totally non-negative matrix, and every totally non-negative matrix comes from one of these networks. So there's a nice combinatorial description of these matrices. And then more recently, the totally positive matrices led to the development of cluster algebras. So Fomin and Zelevinsky were sort of studying these totally positive matrices and how to test for this total positivity property and things of this nature. And it led them to define cluster algebras. I'm not going to be defining a cluster algebra, although it will come up a few times in the talk. So if you don't know what a cluster algebra is, just ignore me when I mention them. Okay. So the next thing I want to talk about total positivity is how it relates to the dual canonical basis. So this is just a kind of crash course summary in what is the dual canonical basis. Essentially for us, it's going to be a set of polynomials in these variables x, I, j, where I and j are both ranging from 1 to n. So you can think of these as being the entries in a matrix of indeterminate, of a matrix of indeterminates. That's an n by n matrix. And these polynomials come from a basis in the quantization where we've added this parameter q and q inverse. And now we say these things don't exactly commute. They have some commutation relations that involve q. And the way we get these polynomials is essentially setting q equal to 1 in the basis that exists here. And what is that basis? So there's sort of a natural involution where we just change the sign on our powers of q. And if we look for polynomials that are invariant under that involution, this basis sort of arises naturally. And why do people care about the dual canonical basis? So this is very important in understanding representation theory. That's unfortunately as much as I can say, since I don't know all the representation theory that goes behind it, but representation theorists use the dual canonical basis as a tool for understanding these things. Unfortunately, even though it is this useful tool, it doesn't have any nice elementary description. Okay, so that's just like quick overview on what the dual canonical basis is. If you miss some of that, that's fine. You can just think of it as here's some polynomials that we care about. And this relates to total positivity in that, so we previously had said a matrix is totally positive if all of its minors are positive. The minors turn out to be elements of the dual canonical basis, and positivity of those particular elements imply positivity of all of the elements of the dual canonical basis. So we now know that any element of the dual canonical basis, if we evaluate it on a totally positive matrix, we'll get something positive. Okay, that was our overview of total positivity. Any questions before we go on to immanence?
How much do we know about the converse of Lusztig's theorem? So like if all the elements of the dual canonical basis are positive, do we know we have a totally positive matrix?
Yes, because if all the elements of the dual canonical basis are positive, that includes the minors, because those are particular elements. And the totally positive matrices were defined as the matrices where the minors were positive. So it goes in both directions. Yeah, good question. All right, so let's introduce these immanents. So switching gears a little bit. An immanent is a function, is a function on matrices, n by n matrices, where if we have some function s that goes from the symmetric group to the complex numbers, what we're going to do is we're going to sum over all permutations, and we're going to stick our function applied to that permutation inside the sum, as well as all of these matrix entries. And so you might have seen a formula that looks like that before. The immanent that we're all used to and work with a lot is just the determinant. So if you say f of w is the sign of the permutation w, then we get exactly the determinant. Another immanent that shows up in a number of places is the permanent. So that's when just f of w equals 1. And in general, the most commonly studied immanence is a class of immanence that includes both of these, which is when f is some irreducible character of Sn. So when immanents were first introduced, really they were introduced in the context of choosing f to be one of these irreducible characters. And there's a theorem by Stembridge that if we have a totally positive matrix, then any irreducible character immanent is positive on that matrix. And so just quick sanity check. So in our two examples here, if f was the sign of w, then we just get the determinant. That's certainly positive on a totally positive matrix. If f was 1 everywhere, then because on a totally positive matrix, all of the entries have to be positive, that means that certainly this permanent is also going to be positive. But it's true for all of the other irreducible characters as well. Okay, so now let's talk about these Kazhdan-Lustzig immanents that were in my title. So the Kazhdan-Lustzig immanent is actually a family of immanents. So they're indexed by some permutations in Sn, where n is again the size of the matrix. And our f here is this whole thing. So -1 to the length of w minus the length of v times this, this term here, where Pxy of q is the Kazhdan-Lustzig polynomial. So we're not putting in directly the Kazhdan-Lustzig polynomial. There's this extra w naught term here, and we're evaluating at 1. And so this might, I should say I have not defined the Kazhdan-Lustzig polynomials. I'm not going to define the Kazhdan-Lustzig polynomials. They are polynomials that give a change of basis essentially between the canonical basis and the dual canonical basis. I'm not going to put up the definition because the definition is recursive and unenlightening, and also because the Kazhdan-Lustzig polynomials are sort of famous for being hard to compute. So the definition really doesn't help us out at all, which is why I won't bother you with it. Okay, but why would one, certainly one can define this thing, why would one define this thing? So I'm going to give you sort of two separate motivations. So the first one has to do with the dual canonical basis. So let's, previously when we were talking about minors, we were taking a subset of rows and a subset of columns. Now let's take a multi-set of rows and multi-set of columns, and we'll essentially get a matrix AB by repeating rows and columns the appropriate number of times. So here's an example. Let's just take M to be the generic 3x3 matrix. If we choose this for our A and this for our B, that means we're going to get a new matrix where we label the rows 1, 2, 2, 3, and we label the columns 1, 1, 3, 3. So you can think of this as sort of, I've taken this matrix, I've repeated row 2, I've repeated row 1, or sorry, I've repeated column 1, I've deleted column 2, and then I've repeated column 3. So you end up with this matrix where, like, for example, if you look at this entry, the rows were indexed 1, 2, 2, 3. So it's in row indexed by 2. The columns were indexed 1, 1, 3, 3. So it's in a column indexed by 1. And so I get the 2, 1 entry of our original matrix. And so this is related to the dual canonical basis and our immanence, because if we take some matrix of indeterminates, the n by n matrix of indeterminates, then we can say our dual canonical basis elements are exactly the Kazhdan-Lusztig immanents that we can evaluate on XAB, where we allow A and B to range over all multisets of n. And then depending on the size of our matrix, we'll get out, we'll have some family of immanents for that, that matrix, and we want to keep all the non-zero ones. Any questions about that theorem? Okay, so that's motivation one for looking at the Kazhdan-Lusztig immanents. Something else we could say that's a little bit simpler, if you'd rather not think about the dual canonical basis, is that we had that theorem from Stembridge where people were looking at what happens to these totally totally positive matrices under the irreducible character immanence. That theorem actually can be broken down. So Heyman proved that every irreducible character immanent is a non-negative linear combination of the Kazhdan-Lusztig immanents. And then because of this fact about Kazhdan-Lusztig immanents being part of the dual canonical basis, we also know that if we have a totally positive matrix, then all of the Kazhdan-Lusztig immanents are positive on that matrix. And so these two things combined reprove Stembridge's theorem, right? So we have our irreducible character immanent is a non-negative linear combination of these things, which themselves are positive. So we've gotten another proof now that the irreducible character immanents are positive on totally positive matrices. Okay, and that's sort of the end of the introduction part. So let's do our 5-minute break there. Let's just, to get back into it, let's just do a quick summary of what we've talked about so far. So we first defined totally positive matrices as matrices that have all positive minors. And we said that this implies that the positivity of all elements of the dual canonical basis. So all elements of the dual canonical basis, when evaluated on a totally positive matrix are positive. And then we use these Kazhdan-Lusztig immanents we essentially wrote our dual canonical basis elements as Kazhdan-Lusztig immanents, where we take some generic n by n matrix, and we maybe repeat some rows and columns, and then we take a Kazhdan-Lusztig immanent of that. Okay, so let's talk about now what Melissa and I were working on. So first of all, we want to generalize total positivity to K positivity. So we say a matrix is K positive if all of its minors of order K, or sometimes I probably will say size K, or smaller, are positive. So here's an example. So again, we can see right away that all of the entries are positive. So all the minors of size 1 are positive. You could check that all of the minors of size 2 are also positive. So M is 1 positive, M is also 2 positive, because we have that minors of order 1 and 2 are positive. But the determinant is negative, so M is not totally positive. So why might one be interested in this generalization? Well, first of all, it's a rather natural generalization of total positivity. You just say, what if we had, what if we had fewer restrictions on our matrices? Instead of requiring all of the minors to be positive, we just require some of them to be positive. But why in particular might we choose this set of minors to be positive? So there's some nice topology that I lied earlier. This is the one other place that total non-negativity rather than total positivity is going to make an appearance, is in this bullet point. Totally non-negative matrices have some nice topological properties. And so if we look at K non-negative matrices, some of these properties still hold, at least in certain cases that have been studied. And then another reason is that essentially the K positive matrices retain some of the cluster algebra structure that the totally positive matrices had. So if you're familiar with cluster algebras, we can essentially like freeze some more vertices and we get sort of a smaller cluster algebra that lives inside our larger cluster algebra, but we still have sort of the same structural properties. Okay, so that leads us to our main question that we're going to be looking at, which is if M is a K positive matrix, when, and we look at MAB, so where A and B were some multi-set of the rows and columns of M, when is it true that an immanent evaluated on that matrix MAB is positive? And so we already answered this question when K is N. So when we have a totally positive matrix, the answer is that it's always true. But so we want to know when is it true in this case where we're being less restrictive about what our matrix is. Okay. So to begin to answer this question, we need to talk about pattern avoidance. So it's possible that all of you know this, but I wasn't sure because the seminar was billed as an applied algebra seminar, not a combinatoric seminar. So apologies if this is a boring slide. But I'm going to define pattern avoidance by example. So here is some permutation W. And I want to look at a permutation that's shorter than W. So here's some permutation that's of length 4, whereas W, or that's in S4, whereas W was in S5. And we can say, does W avoid this pattern? So is W 3, 4, 1, 2 avoiding? And since this is in S4, what we want to look at is all subwords here that of 4 numbers. So I could essentially ignore the 1, I could ignore the 4, I could ignore the 3 or the 5 or the 2. And then I'm going to look at the order relations in here and the order relations in each of these subwords. So let's just color these. So notice here I've colored the biggest thing blue, and then the second biggest thing red, and then the next biggest thing green, and then the next biggest thing yellow. So if I do the same thing for our subwords, I color the biggest thing blue, and then red, and then green, and then yellow, I can notice that I never get the same pattern that appeared in my pattern I'm trying to avoid, the 3, 4, 1, 2. So the answer is yes, it is 3, 4, 1, 2 avoiding, because there's no subword where the numbers in that subword follow the same order relations as the 3, 4, 1, 2. Oops. And here's another example. We can ask if W avoids 3, 2, 1. And let's do the same thing. Let's color the 3 blue and the 2 red and the 1 green. And I could get a subword of length of size 3 by ignoring the 2 and the 4. And if I color that with the biggest thing blue and then the next biggest thing red and the next biggest thing green, I get blue, red, green, and I have blue, red, green here. So we do have the same order relations between 5, 3, 1 and between 3, 2, 1. So W is not 3, 2, 1 avoiding. Any questions about pattern avoidance? Okay, so really the conjecture that led to us working on this project was a conjecture by my advisor, Pylyavskyy, that if M is a K positive matrix and V, this permutation that's indexing our immanent, avoids the pattern 1, 2 up through K plus 1. So in other words, it doesn't contain an increasing subsequence of length K plus 1, then the immanent is positive on M. So as an example, our permutation we had up here avoids 1, 2, 3, 4. So the conjecture claims that if M is 3 positive, this will be true. But it doesn't avoid 1, 2, 3. So the conjecture doesn't necessarily claim that the statement or that this inequality will be true if M is 2 positive. Okay, so then some notation. We're going to take P to be some subset of Sn, and then gamma sub P is going to be this n by n array of dots, where the dots are in the entries given by all the permutations in P, and then the other spaces are just left blank. So here's an example. Let's pick W to be this permutation, 2, 4, 3, 1. And we'll pick P to be the whole Bruhat interval from W to W naught. So that includes these 4 permutations. And if we want to construct gamma sub P, or gamma sub interval from W to W naught, what we would do is we'd look at this first permutation. Okay, so we have 2, 4, 3, 1. So that means in the first row, we're going to put a dot here in the second column. Then we'll put a dot in the fourth column, then the third column, then the first column. So that's what we're getting from 2, 4, 3, 1. From 3, 4, 2, 1, we're going to get a dot here in the third column, then here in the fourth column. There was already a dot there from the previous permutation, but that's fine. Then we get a dot for 2 and 1, and so on. And if we look at a collection of all of our dots, we get this. So we have some blank spaces in our grid. And then we're going to have this object M restricted to gamma sub P, which is the matrix M, where we change all of the entries to 0 wherever there's no dot in gamma sub P. So you can see here that if M was just our generic 4x4 matrix, we've replaced these entries with zeros because there were no dots here. And we've replaced these entries with zeros because there were no dots over here. Okay. So our main theorem then is that if we have a permutation that is 1, 3, 2, 4 and 2, 1, 4, 3 avoiding, and the largest square region contained in gamma sub the interval from V to W naught is size k by k. And what I mean by that is if we look back here, we have a like 2 by 2 square of dots right here, but there's no 3 by 3 square of dots, right? We'd need there to be a dot here and there isn't. So the largest square region in here we would say would be 2 by 2. Okay, so if we have a permutation that avoids these two patterns and the largest square region contained in here is size k by k, if we have a k positive matrix and we have an immanent that's not just always 0, then the immanent is positive on MAB. Any questions about the main theorem?
The first, I mean, are you guessing that there's a pattern avoiding permutation condition which is going to describe which are positive, which are not positive? Or are you, I mean, I guess I'm wondering, how do you come up with what the condition is? Are you just looking at a bunch of data, or is there something else that's motivating how you're making that description there?
We're going to do a sketch of the proof next, so you'll see. I don't know if that's a satisfactory answer at the moment, but I guess let's just go into the proof sketch. So, so the first thing that we used is, so this is, I wrote this as one theorem, but it's really coming from two separate theorems. So this first result here by Kazhdan-Lusztig says something about how the Kazhdan-Lusztig polynomials relate to the cohomology of Schubert varieties. And then this second result by Lakshmi Bai and Sandhya says something about the cohomology of the Schubert varieties. And so taking them together, we can say if W avoids these two patterns, then we do have a good formula for the Kazhdan-Lustzig polynomials. So remember I'd said previously that the Kazhdan-Lustzig polynomials were really hard to compute. And this was like one of the main difficulties in tackling this problem, is that we didn't know how to deal with these Kazhdan-Lustzig polynomials. And as one does in math, sometimes when something is hard to figure out, you say, oh, well, let's just look at a smaller case that's easier to figure out. So in this particular case, we do know what the Kazhdan-Lustzig polynomials are. And so that actually gives us our two patterns that we're trying to avoid. Back when let's go back and look at the definition of the Kazhdan-Lustzig immanents. Yeah, so there was this W naught that showed up here. And so that's why the two patterns we're avoiding are not the same as these patterns, right? They're inverted. This 4 became a 1, the 2 became a 3, and so on. That's because of the multiplication by W naught. But so if V avoids these two patterns, then we can say we have this much nicer formula for our immanent, where we just have this -1 to the length of W in here, and we had a -1 to the length of V outside. So this looks really a lot like a determinant. It's clearly not fully a determinant, because we're only summing over the W's that are greater than or equal to V, but it looks sort of similar to a determinant. And so we were trying to see, could we write this as a determinant somehow? And so we have a proposition that follows from work of, I'm going to butcher this, I think Sjøstrand. So that says that if W avoids these 4 patterns, then it's actually true that this object we defined, M restricted to gamma VW naught, that the determinant of that matrix is exactly that expression that we were looking for. So essentially, there are no additional terms that show up here that we don't want. And so we can combine that lemma from this slide and the proposition to get our to get this lemma that says now, okay, we can rewrite this immanent as -1 to the length of V times the determinant of a matrix that's our original matrix, but just some things zeroed out. Okay, and so now that our immanent is instead written as a determinant, we can use Lewis Carroll's identity to complete our proof. So Lewis Carroll's identity says that there's this relationship where if we take a pair of rows and a pair of columns, the determinant of a matrix times the determinant of the matrix where you've removed those rows and those columns is equal to like this other expression in terms of determinants of matrices where you've removed one of the rows and one of the columns. So instead of M here, we want MAB. And so what we needed to check was, first of all, that all of the other determinants in the expression, so this is going to be our determinant of MAB, so that all of the other determinants, there's like some nice choice of rows and nice choice of columns, where the other determinants are either 0 or they're Kazhdan-Lustzig immanents of permutations that meet or indexed by permutations that meet our hypotheses up to sign. So essentially, we're doing some inductive argument where we say, okay, if we know this is true for matrices that are of a certain size, let's try to prove they're true for matrices that are larger. Because all of these matrices, so if this is n by n, then this would be n minus 2 by n minus 2, and these would all be n minus 1 by n minus 1. And so then we also need to prove essentially that this guy and the negative of this guy have the same sign. We have some and then we have some dividing by 0 concerns that we need to deal with. So there's a couple things we need to check are non-zero. So does that, Mike, does that answer your question about sort of where these conditions come from I guess maybe I didn't fully address. So these conditions are sort of for our convenience in that we only knew how to deal with the Kazhdan-Lusztig immanents that where the permutations avoided these patterns. This condition about the k by k region was essentially when we do induction, we'll eventually get down to a determinant that's size k by k. So if m isn't k positive, we can't guarantee that that determinant is positive, where we don't know the sign of that determinant. So that's where this other kind of weird condition comes from.
Right. Yeah, it does. It does at least the first part, and then the and the other part that I wasn't sure about was it an if and only if or an if then, and you're using the fact that you've got a simplified form for your pattern avoidance.
Yeah, it's definitely an if then, not an if and only if. Okay, so yeah, okay, just to wrap up a couple of loose ends. So we had said previously that this was the conjecture that really motivated our work. And so we wanted to know, we kind of veered a little off course from that. We wanted to know how our result compared to this conjecture. So our result is strictly weaker than this conjecture because if a permutation V meets the hypotheses of the main theorem, in particular that condition about the k by k square, then V has to avoid this pattern. If this pattern existed, then there would be a square of size k plus 1 by k plus 1, which is maybe not obvious to see. You have to work with them for a little bit, I suppose. But so our theorem supports the conjecture, but is weaker than the conjecture. So if anyone out there thinks this is interesting, this is still an open conjecture. Another thing is that we have these, yeah, so as we were just talking about, we have these sort of two separate conditions on our permutation. One is this pattern avoidance condition, and then the other one is this weird, the graph of the interval up to W naught has to not contain a square that's larger than k by k. And so we were wondering maybe we could put this all in terms of pattern avoidance. And so you can, the short answer is you can, but it's not nice. So here's one corollary. If M is a 2 positive matrix and W avoids these 4 patterns, then the immanent indexed by W is positive. However, this doesn't like scale nicely in any way. So already, if we say if M is a 3 positive matrix, what patterns do we need to avoid to guarantee this? We already have 11 patterns just for k equals 3. So there's, it's making a text box. That's not what I want. Yeah, so there unfortunately isn't really a nice pattern, like a nice characterization that's completely uses pattern avoidance.
But for each k, is there one?
Yes, for each k there is one. It just becomes a lot of patterns very quickly, so I don't know that it's very useful. And then just a quick note on cluster algebras and also what we're working on now. So this corollary can be proven just as a corollary of our main theorem, but it also could be proven in a different way. Also have a different proof that uses completely cluster algebras or methods from cluster algebras. It is conjectured that cluster monomials are a subset of the dual canonical basis. So we're looking at elements of the dual canonical basis and we're trying to determine when we know those elements are positive. Certainly if they're cluster monomials, we know they're positive. So right now we're working on trying to determine how much of our theorem can be reproven using cluster algebras versus using these linear algebra techniques that I showed you. And I am 3 minutes early, but I'll end there. And here are my references.
Awesome. Let's thank Sunita for her amazing talk.
Yes. Sure.
waiting for Nantel. Do you want to try Nantel? Or are you trying Nantel? Yeah. Hey.
Did it
Cool.
work?
Yeah, it worked.
Oof.
Thank you.
That works, but I was trying to like, well, maybe we should all be just clapping louder so that we don't have it this week.
Oh, now my iPad is playing other move.
Are there any questions? I guess while people are thinking, I do have a question. So you know how you were saying the numbers get unwieldy when you get higher?
Mhm.
Okay. Have you looked into the OEIS to see if like there is a pattern in those numbers?
Oh, no, I haven't. That's a good question.
Because that'd be cool to see. Because then potentially it might actually be like tangible.
Yeah, so the reason that the numbers get larger so fast is that essentially if you have if you're trying to avoid a 3x3 square, you can sort of get like a 3x3 square where like things are in order, or there could be like one inversion, or there could be two inversions. And so there's like not that many things to deal with, but like the larger the square is, right? Like we sort of start with like, oh, everything's like along the diagonal in this square, and then just add more and more inversions. So that's why there's so many patterns to avoid. But that does seem like it's possible that there might be an entry on OEIS for that.
And then for like the k=3, you said there's 11 patterns it has to avoid.
Mm-hmm.
Do the 11 patterns contain the 4 patterns from k=2, or does it build off of the previous k, or are there sometimes things that like are they subsets? Yeah. Does that make sense what I'm asking?
Yeah, so they build on them, but in not in like a subset sort of way. Like, so for example, this one needed to avoid 1, 2, 3. The next one will need to avoid 1, 2, 3, 4.
Okay.
But yeah, so they're not like subsets, but they do sort of build in some way. Oh, is there something in the chat?
Yeah, so Raleigh, I'm assuming I'm saying your name right, sorry if not. He's asking if the conjecture may be easier to solve for matrices with integer or other entries.
Yeah. I mean, we've mostly just been considering integer entries. But I think the main difficulty with the conjecture is this, like, how do you deal with these Kazhdan-Lusztig immanents, and so, or these Kazhdan-Lusztig polynomials. And so I think I'm not sure if the entries of the matrix, or like where the entries of the matrix come from, if that plays that big a role in like the difficulty of the conjecture. But it's certainly possible that if you restricted it enough to, like that it might help.
He says, they say thanks. Are there any other questions?
In general, can you expect that k-positivity, the k-positive matrices are going to be positive on the immanence? Is that going to be characterized by a pattern avoidance condition? Like right now, you're actually saying it's only if it satisfies these conditions, then it's. But you actually know that, let's say I'm looking to characterize it in a precise condition. Is the answer something that can be expressed in terms of pattern avoidance?
I don't think we know. I guess that's not part of the conjecture as I stated it, but I guess that would be sort of part of the conjecture, is that this would be like a good characterization.
Yeah, I mean, I guess one could tell if you could generate like lots and lots and lots of data, and then you'd say, hey, look, it looks like this. But I imagine that kind of your limitations are that you can't generate lots and lots and lots of data, right?
Yeah, it gets, just because the polynomials are so hard to compute, you just can't get that much data. You can only really do like some, like small cases.
I have another question actually. So like, in the summation you had for the immanence, when you're looking at the Kazhdan-Lusztig, and you have the W naught in front, has anyone looked at what happens if instead of putting W naught in front, you just put some arbitrary element instead? So like you do
like if I
P's,
picked my favorite,
yeah,
maybe I'm in S4 and my favorite permutation is 3, 4, 1, 2. If I put a 3, 4, 1, 2 here instead.
yeah.
Um,
So like kind of generalize this one step further by like multiplying by choosing what to multiply rather than multiplying by the top element.
yeah, I don't think so. I think a lot of the work with Kazhdan-Lusztig immanence has, like, a lot of the proofs rely fairly heavily on representation theory. And so in that case, you wouldn't have the like representation theoretic like interpretations of the Kazhdan-Lusztig immanence. So proofs might get harder. But it's certainly something one could do. It just might be hard to prove anything.
That works. Are there any other questions? If not, let's thank the speaker again.
Better?
Thank
Yes.
you for having me.